on your review sheet, I think I went ahead and made a diagram like this. The thing that, kind of the hole in the fabric of space and time, actually that's called the singularity. Okay, and then out from the singularity, we have something called the event horizon. That's the event horizon. I'll put H for horizon. And then the Schwarzschild radius is actually kind of like that. I'll put SR for Schwarzschild radius. It's kind of the distance from singularity out to the event horizon. So the problem here is if you are a person here on the, what we say, the inside of the event horizon, then you're never escaping. That's problematic, okay? If you are a person here outside the event horizon, you have a fighting chance of escaping, okay?
Are you saying if there's a black hole that's a centimeter, like it'll suck people into it? Even
Well, see, the thing is if you are, now if you're too close, like for this guy probably, I might have it drawn too close, this guy might be sucked in, okay? Because in the vicinity of the event horizon, kind of the fabric of space and time is disturbed. But my thing about it, if you're over here, there's a good chance that you're not even going to care that there's a black hole, as long as you don't wander that way. Okay, that's kind of weird. So if the sun actually turned into a black hole, you know, we took the Earth and shrunk it into, basically, the thing about shrinking something into a black hole is you're changing the matter. The matter, we said, of a neutron star is basically neutron soup. Protons and electrons have turned into neutrons. The thing about black holes is basically it's compressed farther, so neutron degeneracy doesn't support it. So it basically creates that hole in the fabric of space and time. But remember a minute ago I had that little green man, and I said if you're far enough away, you won't even, life will be normal. So actually, from what I've read, if the sun were to basically squish down so that its matter turned into the matter of a black hole, the Earth would just continue to orbit. We wouldn't have that solar radiation, but kind of the gravity that we feel that's created by the sun now would be the same gravity that we feel when the sun turned into a black hole. So I think that's kind of interesting. So I have two scenarios about a black hole, falling into a black hole. So it goes something like this. We actually are in the spacecraft with a blue light, the blue time right here. Okay, so we're in this spacecraft right here. Okay, the black part starts what we call the event horizon. I'll make a little red dot where singularity, oops, that's not red. Okay, that little red dot, that's singularity. Okay, so we have singularity, we have the event horizon. Okay, we're far enough away from the event horizon, we're in this blue spaceship. Okay, we're not going to fall in. Or it's not a blue spaceship, but basically we have a clock on it that has blue colors. All right. So what we do then is we send a probe, an unmanned probe, in the other spacecraft. Okay, and we're going to send it towards the event horizon. Okay, you know this can't end well, right? Okay, and it's well documented. Einstein actually can prove these theories that I'm going to describe to you. Okay, but according to Einstein's special theory of relativity and general theory of relativity, here's what happens, okay, as we send that unmanned spacecraft towards the event horizon. Remember, in the vicinity of the event horizon, the fabric of space and time is really warped, really warped. The black hole itself actually has an immense amount of gravity in a close proximity. That's what warps the fabric of space and time. So two things that I kind of want to talk to you about, or have on my slides. One thing is called gravitational redshift. So can you see where the clock, instead of it used to be blue when we sent it that way, but now as it approaches the event horizon, it's red? Literally, that's what would happen. It's called gravitational redshift. And I think of it this way. Basically, anytime you see a clock like that, basically that clock is sending photons to us. And we're saying, oh yeah, I see a blue clock. So basically, as that object gets close enough to the black hole, the photons have to climb out of this, what's called a gravity well. So basically, they lose some of their energy as they climb out. So instead of being that pretty blue that we sent, basically they lose some energy. And what color is when you go from blue, when you lose energy, what color does it go to? It goes to red. Okay, it's lower energy. So actually those photons lose energy. So that's called gravitational redshift. And anything like if a neutron star can give you gravitational redshift. Anything that's got a lot of gravity to it. The other thing is called time dilation. So you see the clock, not only is it red, but also notice the time it's ticked off is 15 seconds instead of 50 seconds. 15 seconds instead of 50 seconds. So remember, this is actually from our perspective. So from our perspective, we see it go red, okay? And then we also see less time, i.e. time will slow. Time slows down. Now, does it slow down for that? No, it does not slow down for the object that's approaching the event horizon. But from our perspective looking in, their time is unfolding slower. Time dilation. Time dilation is affected by gravity, like this. Time dilation also occurs when you're going at high speeds. It also occurs, and that's an Einstein thing. And so here's the deal. Actually, aside from black holes, going at high speeds, we've seen time dilation. If you put a clock, an atomic clock, a really accurate clock, okay, here on Earth, and then you have another clock up in a jet airplane, okay, and then you let the jet basically do its thing. It's going to go really fast, right? And when it gets done, you compare clocks, and actually time has ticked off less time. Time slowed down compared to our time. Like, really? I'm like, yeah. Is that not cool or what? Time dilation. The moon is another one. The moon's not a black hole, but the moon a little bit, you say the moon would be less massive? Yeah, there's no gravity, it's less massive. So actually in that case, it's kind of the opposite. The Earth, more gravity, more like a black hole in a sense. So actually time goes more slowly here on the Earth than it does on the moon. Time goes more quickly on the moon. So it's a gravity thing, and it's actually, if you're so that is so cool, time dilation. But now there's another idea. So let's say that you push your colleague overboard and you say, no, go ahead. Go check out this black hole, right?
You go first.
You go first. I want to watch. Okay? So, and not only that, but it's kind of like the movie Gravity, where you don't even send him in a spacecraft. You basically have him go without the aid of a spacecraft. Okay? Yes. So here's the deal, and they call it kind of tidal forces. Well, I'll get to that. But gravitational redshift, what's going to happen? Okay, he might be in a white space suit, but as he gets closer to the black hole, you're going to see him change colors. Okay? Actually, he might be red down here and white up there. Whatever's closest to the black hole is going to be more gravitational redshift. He might be a rainbow thing at that point. Right? Let's see. And here's the deal. Time, from our perspective, his time unfolds slower and slower and slower the closer he gets to the event horizon. So here's the deal. As he is basically almost at the event horizon where the fabric of space and time is torn, he basically, it'll like look forever. He doesn't go into the black hole. He's like, dude, are you ever going to cross the event horizon or what? Like, yeah, a long, long time. Hover forever. Okay. So, but from his perspective, he's gone. Okay, we've talked about the acceleration due to gravity. The Earth has, you throw something up and it goes faster and faster and faster. Acceleration due to the gravity of the Earth. Well, think about the gravity of the black hole. So he's going to go faster and faster and faster from his perspective. That is just amazes me. Okay, so yeah, he's a goner. Okay. But here's where the word spaghettification comes in. So I've watched Neil deGrasse Tyson do like a little monologue on this, really short, but it's like, there's different ways to perish, for your life to be gone, electrocution, different ways. So spaghettification actually is what happens when you die via a black hole. So the way it's like spaghettification is like this. Basically, here at his feet, this pole is great. It's the greatest. I don't mean in a good thing, okay? In fact, Neil deGrasse Tyson called it kind of like cosmic yoga at first, like, oh, it's stretch, I can do that, okay? But actually that's not good because it's kind of a delayed pull, and so the pull here basically kind of extrudes you out into a stream of atoms that are kind of lining up to fall through the event horizon into the black hole. It's called spaghettification.
Do they call it that because you look like a spaghetti noodle?
I think so.
Okay.
Does it say who woke up and decided?
I don't know. I don't know the origins of that term, but it's out there. It's out there on the internet. So how do we know that black holes are out there? On Friday, we'll start talking about galaxies, and we already know that the Milky Way galaxy has a supermassive black hole in its center. We're talking about stellar black holes, which are basically created kind of beyond a neutron star. It's compressed even more to create a stellar black hole. Okay. Well, this is my analogy. Okay, you can't see a black hole because nothing crosses the event horizon. It's black, right? It can't shine. Black holes do not shine. I have heard or watched documentaries that if you were to peek inside the event horizon, it would be very bright in there. I think I'm thinking of this right. I know. Because I don't know if that's right or not, but remember what happens at singularities, basically matter is mushed into something that is very strange, I think. But the example I'm going to show you for a stellar black hole is basically it has a companion. We talked earlier a lot about kind of these companion idea. Basically, remember, if you have a white dwarf and a companion, the companion can dump on the white dwarf, okay, and things can happen. If you have a neutron star and a companion, again, okay, things can dump from the companion, especially if it's in this red giant stage. It can dump on the neutron star. So we have here a black hole, okay, and its companion. So again, you see this thing we've been calling an accretion disk, okay, kind of the stuff that's in Q to basically. The thing about accretion disks, and in this case we have, with a black hole now, instead of a neutron star or white dwarf, we have even more gravity that's basically pulling this stuff in. So we have more friction, okay? What can happen is it can create X-rays. Remember, kind of on the spectrum of energies, we have gamma rays, X-rays, ultraviolet, visible, so it's pretty intense. So we have X-rays being created in the accretion disk here. A constellation I think we've talked about is the Northern Cross or Cygnus the Swan. Same thing. You kind of see it in yellow up there. So actually, we have a normal star, and our normal star has a companion that is emitting X-rays. It's not glowing, okay, in a sense, but in the accretion disk, it's emitting X-rays. So the fact that it's not luminous, we can get a fix on its mass and its volume, and we can know that matter is crunched down to a stellar black hole. So, okay. One last thing. So remember, X-rays, more energetic than X-rays are gamma rays. So actually, here are some gamma ray bursts that are thought that at the time that a stellar black hole is formed, it's thought that actually these signatures are created. Okay? Very good.